Hello and welcome to Mostly Climate. I'm Clare Nasir. In this episode, I talk to Professor Lizzie Kendon, Scientific Manager and Science Fellow here at the Met Office. Lizzie recently published a remarkable report looking at the effect of climate change on the frequency of extreme rainfall events. This work and data will contribute to the latest update of the UK climate projections, an incredibly useful tool for scientists, policymakers and planners. We start the conversation with an explanation of the science and methodology behind the report.
What we've done is we've produced some projections of very high resolution, allowing us to look at how climate is evolving from the past to the present and right out to the end of the century, out to 2080. So it's a continual 100-year time series, which is really allowing us to explore how changes in extreme rainfall will manifest through time. It's both understanding the underlying climate change signal, but how that kind of interacts with variability to see how it is we will actually see extreme rainfall changes materializing as we go through time at the local scale.
Now, this is critical to what happens, particularly, I'm going to say, during the summer months and convective systems and rainfall. But let's just backtrack a little bit, because you're saying it's a fine resolution. I mean, I've been working in weather now for 28 years, and this is something that you maybe couldn't have done even 5 years ago. Am I correct there? Is this level of information, you're working with technology and with innovation as it's really powering on?
Yeah, these are a new, unique set of projections. So we're actually using the weather forecast model on a climate timescale now. So we're able to say, look at how rainfall or temperature is changing on every single 2.2 kilometre grid box across the UK for every hour for 100 years. So there's an incredible amount of detail here. Just to put it into context, we've had to split these up as a series of 20-year simulations because they are so expensive, and then stitch them together. And each 20-year simulation takes 6 months to run on the supercomputer here at the Met Office. So you get a sense that this is really pushing the technology, and we certainly could not have done this a few years ago. But it's really important for us to have this level of detail, because we made a step change in terms of our ability to represent the processes that are really important for local flash flooding type events. So, what I'm talking about here is essentially convection, which is the key process behind many of our extreme weather events. And we really need this high detailed simulations to really capture those with a degree of realism so that we have confidence in what we're therefore projecting into the future.
Let's just backtrack a couple of years. And I remember an extreme storm across London where there was so much flooding and the imagery was just crazy. And it's this type of event that needs to be captured and understood, because as we head towards the mid-century and beyond, the frequency of these type of sort of deep convection thunderstorms and the amount of rainfall encapsulated, embedded within the system is going to become more frequent.
Yes, so the sort of event we're talking about is the event we saw, for example, back in July 2021 in London. Then we had about a month's rainfall fall in 3 hours over Kew Gardens. It led to, tube stations closed, widespread disruption. And then a couple of weeks later, there was another event, very similar, very intense downpour. We had 2 hospitals flooded. So these are the types of events that we're talking about here. They're important in urban areas and small catchments where we're particularly vulnerable to water levels rising very rapidly, which can lead to these sort of flash floods. And for these types of events, we can now look in these local projections and see how they're going to change through time. And kind of on an average sense, we can see a big increase in the likelihood of them. By 2080, we expect them to be 4 times more frequent than they are in the 1980s under a high emission scenario. So that is a really big change if you think about how devastating these events can be. I think it's important to say this is for a high emission scenario. So we're talking about here the RCP 8.5 scenario. So the changes aren't inevitable, and in a way they are kind of both helping us to, identify what the consequences would be if we did not cut our emissions. Obviously, if we did follow a lower emission scenario, then actually the changes that you're talking about here would be less. But nevertheless, we are talking about potentially significant changes to rainfall of this type, whatever scenario we're following. But a 4 times increase is really big. And if we compare it to, say, the sort of climate models that we were able to run then the changes are larger than they're predicting. So, what was seen as a high resolution model produces a change of about two to three times, whereas here we're talking about a 4 times increase in these events by 2080.
And so that's pretty much, I know the phrase hope for the best, plan for the worst. And this type of information is vital for city planners and beyond.
Yeah, so a lot of urban drainage systems that we currently have are designed based on historical rainfall rates. They don't have the capacity to cope with the sort of increases that we're talking about here. These new projections show us that for every single degree of warming, we're expecting a 5 to 15% increase in the intensity of these heavy downpours. Even for, more moderate emission scenarios, we're talking about quite big increases in the intensity of rain that the urban systems have to handle. So, we're talking about needing changes in designing of the infrastructure in cities, having better drainage systems. There's lots of local authorities and flood planners who need to have this kind of level of information moving through time so that they can really plan for the future. So, these simulations are kind of giving us a window, a kind of an envelope of change as we move through time. So we can plan for the most high likelihood, the upper estimate, but also give us a sense of what, the changes could look through time. So we might not always have very heavy rainfall events. With some years we will have very few, but it gives us a sense of how that envelope of how the climate will change through time.
Were there any surprises to the solutions to the models as you ran them through the last 6 months, a year, etc.?
So, we expect heavy rainfall to increase as the climate warms. It's primarily driven by the fact that the atmosphere can hold more moisture. So, in a sense, we expect a sort of increase in these extreme events. But what was surprising was the nature with which the changes actually manifest. So, you can have, a similar number of events occurring year by year for a period of time, and then you can actually get very rapid transitions occurring where you get suddenly a lot more events occurring and records being broken by quite a margin, and then you can have a sort of pause and a period of time when there aren't very many events, and those pauses can last for a surprisingly long time as well. And the reason you get this kind of sort of almost erratic behavior is because you have modes of variability within the climate that occur on all sorts of timescales interacting with this underlying trend. And when all the phases of variability come together, you get this enhancement of the increase, and you can see a real sudden transition to behavior you haven't actually witnessed in the observational record, say up to that point. So it has, the potential for us to be prepared in the future. So we can't just use our observational record up to now to give us an indication of necessarily what we might expect for the coming years, because we can get these rapid transitions in the numbers of these extreme events that can occur.
So pretty much there's no climatic norm anymore. There is much more of an erraticness to the trends that you're seeing, which in itself is an interesting thing to be diving into and looking at. Looking at it's such a long period of time. 100 years, that's a bigger picture, isn't it? Is there anything else within that local scale that you would love now to study?
Yeah, I guess this study that we've been looking at here is focused on local rainfall. Particularly, we've been interested in record-breaking events because that often gets public interest and really gets attention, and people are always interested to know if this event is connected with climate change. And obviously, it has big consequences for aspects of society. But there are many other things that we could look at, and we will be looking at through time. So we're interested in drought, for example, the occurrence of heat waves. These projections allow us to explore all different types of weather that we experience here in the UK and how those might evolve over the coming years and decades. Extremes have happened in the past and they always will happen. I guess it's how the likelihood of those are increasing, and indeed whether we can actually observe that in the observational record as we go through time. In terms of really local extreme events, I think that certainly in terms of rainfall, it is so variable. It's probably one of the most difficult variables to really actually discern the impact of climate change. And if we start to look at something that's more aggregated in space and time, so instead of, records of local hourly rainfall, we might say, well, what's the UK average winter mean rainfall? How does that look? And records in that are much more strongly influenced by climate change. So we can say that the occurrence of those sort of records are going to be 70% more because of climate change, whereas the really local, it's only sort of 40% more. So the wider you look and the more you average over things, the more the signal is increased above the noise. So you can actually discern the influence of climate change more easily. But for these really local events, which is what can have the biggest impact in many ways, it's quite a challenge to really see the evidence of the climate change above the variability.
This is real cutting edge research. Has it been done anywhere else in the world to this degree, over 100 years with a grid of 2.2 kilometres?
We're one of the first to be able to actually have the long continuous information, and we've got actually 12 simulations here as well. So that is important because it allows us to really, every single individual realization, which is obviously one of which we will actually observe, evolves quite a little bit differently, and the different variability is captured a bit differently. And so you need to do multiple realizations, I suppose, to really try and identify what the underlying change is. So that's an important part of what's been done here. So it's 12 100-year projections. And although we have been able to do long projections with climate simulations at coarser resolution, and that's traditionally what we use at these sort of resolutions where we're down to the weather forecast model resolution, we haven't been able to afford to do that until now.
Through your results, was there much variability across the country?
Yes, there is actually. So increases are generally greater in the northwest of the UK and less in the south. So for every degree of regional warming, we expect about a 15% increase in the intensity of rainfall over the northwest and Scotland, and about a 5% in the south. So there is a variation across the country. It's primarily driven by the availability of moisture. So as the climate warms, we expect the atmosphere to hold more moisture. And that's one of the basic reasons why rainfall increases with climate change. But how that moisture availability actually manifests locally depends on a number of different factors. So not just the temperature and the holding capacity, but how much moisture is brought into the region. And that varies across the country. And that's why we get this kind of north-south gradient in changes.
Can you explain to me on a more of a stripped back, simple way, the nature of this erraticness of the intensity of the rainfall through a long period of time?
Yeah, so I think a nice analogy for this is waves coming up a beach on an incoming tide. So we can kind of see the incoming tide as the kind of underlying climate change signal. And then waves can come in a series of larger waves, and then there's lulls in between. And this is very much similar to this different modes of variability in the atmosphere occurring on different timescales, such that we can have periods of time when the extreme events, in years of extreme events, clustered. So we have a lot of extreme events, we have a rapid intensification, we get quite a few new records set, some by quite a margin. But then we'll have a pause, which is a bit similar to the lull in the waves coming up the beach, where it's a chance for ecosystems to adapt. Maybe it's a pause, but you can also maybe see it as borrowed time, because that once that pause has come to an end, you may well then get more extreme events on the way, because there's this underlying trend, like the tide coming up the beach, that is underneath all of this.
This is a passion project for you, I'm sure, because you've obviously been really part of it from beginning to end. Were you excited when the results came out? Were you just trying to get your hands on it and understand what was going to happen?
I suppose when I saw the sudden rapid transitions you could get in one of the realizations, that was kind of quite an eye-opener for me, because it wasn't what I necessarily expected. I expected sort of variability and things to be, jumping up and down a bit, but I didn't expect to see these almost rapid transitions when you suddenly go into almost a different regime. I don't think we fully understand that. There are a number of possible candidates for why that might happen. There are changes in the drivers sort of sea ice in the Arctic as a candidate, where the Arctic goes ice free. There are drivers in the ocean that have these sort of long-term committed changes that suddenly can induce us into a different state. But to actually see something like this in the local rainfall record, something as impactful as how much hourly rainfall I'm going to get in my particular little patch any time in a year, the maximum I'm going to get, that's really quite extreme measure. We do see some evidence of this transitioning behavior. And I think that was an eye opener for me, because I thought, actually, we've got, this is a really important message to get across to people, how this might manifest. And so that people are aware of that, so that when they're planning for, the future, they really, do capture the full range of possibilities that might be coming each year.
Just tell me finally about the time scale. You say 100 years. So where does it go back to and where is it going to?
Okay,
What's the
so it
boundary?
starts in 1980 and then it runs for 100 years from then up to 2080. I mean, the reason we do some simulations in the past climate is so that we can validate the model against observation. So really important for any study like this is to question how good the model is. Is it really producing, events of this type that we're interested in a way that is consistent with the observations of the past? That's why we start back in 1980. So we've got this period of time when we can assess how well the model's performing, and then we look into the future from there.
Professor Lizzie Kendon, Scientific Manager and Science Fellow here at the Met Office. My thanks to Lizzie, and you can find out more details about her rainfall report in the description accompanying this podcast. For now, though, I'm Clare Nasir. Thanks for listening to Mostly Climate.
Mostly Climate is a podcast by the UK Met Office. For the latest weather conditions where you are, download the Met Office weather app.